All right, so when we're using Kirkoff's laws or Kirkoff's rules to figure out what's happening in a complicated circuit like this, the idea is, right, we know Kirkoff's rules, first of all, right? The current going into and out of any junction has to be the same, right? So what total current going in and the total current coming out of any junction has to be the same. And the total voltage, the net voltage around any loop, whether it's any loop, right, starting at one point and then working our way back to that point, no matter what the loop is, the top loop, the bottom loop, the outside, whatever the loop is, always adds up to 0. Okay? Those are our two Kirkoff's rules. So how do we approach this problem? All right. First thing I always do when I approach this problem is just conceptually try and figure out what direction all of the currents are going. Right. So in two of the three wires here, I think that's pretty straightforward and pretty obvious in this example. Right. On the bottom wire, what direction do you think the current is going? Left to right or right to left?
Left to right.
Left to right, good, because right, our battery, right, this is the negative terminal, that's the positive terminal, so that's the high potential. So it's going to go out of the high potential and work its way back to the, so I agree. We'll call that one I3, because it's the bottom. We'll call this one I1, I2, and I3. All right? What about this middle wire? You think it's going left to right or right to left?
Right to left.
I agree. In this case, right, this is our negative, that's our positive terminal, there's our high potential. It's going to leave the high potential, fall out of the high potential. So that's I2. The question becomes, what direction is it going through the top wire? Right, because if we look at it at this junction right here, right, if we look at this junction right here, we've decided that I2 is going into that junction. I3 is coming out of that junction, right? This is I3. Right, the current. The question is, what's happening here with this current? Is it going this way around the loop or this, is it going out of this junction or coming into this junction? Anyone have a guess? Ultimately, it doesn't matter when we're doing the problem. What will happen is if we guess wrong, the current, when we solve for that current, we'll end up with a negative value, which just kind of tells us we guessed wrong and it's going the other direction, right? But I think it generally, if we can get it right, it makes it a little bit, this much easier. All right. So when I look at this, my thought is this, right? This is the positive, this is the high potential for this battery, which is kind of connected to the low potential for this battery, right? But this low, because this is 80 volts, is lower than this high, which is only 45 volts. So my guess is that this is a low point, is lower, and the opposite happens on this side, right? Here's a high point that's 80 volts and a low point that's only 45 volts. So this over here is probably a higher potential, relatively speaking. So my guess is it's going to go from the high towards the low through that wire, right? Like I said, ultimately, if we guess wrong when we solve for that current, we'll just get a negative value when we know we guessed wrong, right? But I think it works out easier if we guess correctly. It's not a huge difference, Just a little bit easier. Okay? All right, so I'm gonna guess that it's going this way. Right, so it's going that way. So this is I1, right? I think we can be pretty confident about I2 and I3. I1 is a little bit more of a guess. Okay, so now we have three unknowns, right? We have current 1, current 2, and current 3. So if you have three unknowns, we need come on now. Mathematically, if I have three unknowns, I need three. Nothing. You guys are killing me, right? If I have three unknowns, I need three equations, right? Three unknowns is three equations. So where are we going to get our three equations? We're going to get them for Kirkoff's rules. One of the equations always has to be the current equation. Okay, always has to be the current equation. So I'm going to look at this junction point right here. And in terms of current, I have I1 going in, I2 going in, and I3 coming out. All right? So in terms of current, I'm going to say I1 plus I2 equals I3. Right? The sum of the currents going in equals the sum of the currents going out. Good? All right. So that's one of our three equations that we're going to need. The other two are going to come from the loop rule. Remember, the loop rule tells us that as you go around any loop, the total voltage, the total net voltage is 0. All right, so, all right, now we'll do a loop. Pick a loop. Outside, top, or bottom. Doesn't matter which ones. We have to do two of them because we need three equations total, right? We already have one. So we need two of the loops. I don't care which one. Make a choice. Somebody make a suggestion. Outside, top, or bottom?
Top.
Outside.
Top. And Shayna said outside. So we'll do those two. Max said top. Shayna says outside. So that's what we'll do. So let's start with top because Max was this much sooner. Here's our top loop, right? Okay. I'm going to go around the top loop. I personally always like to start at the negative terminal of the battery. It doesn't matter, but I could, all right, so I'm going to work my way from this point right here around the top loop and get back to that point. Okay? So I'm going to go this way. So we're going to go from a low to a high. So I'm going to increase as we go from this point. We're going to increase 45 volts. So we have plus 45 volts. Whenever we go, the current is going in the same direction as we are in our loop across a resistor. We're going to drop a voltage. All right, so here we have gained 45 volts. Now we're going to drop current times resistance, I2 times 40. So I'm going to drop 40 I2 volts. Continuing around. Now I'm going in the opposite direction. Going in the opposite direction screws things up, so we, instead of dropping a voltage, we gain a voltage. Right? Here I'm going with the current, so I'm dropping a voltage. Going opposite the current, I'm going to gain a voltage. So I'm going to gain 30 I1 volts. And now I work my way back and we're back to where we started. So that is equal to 0. Right? If we think about it this way, right, I kind of talked about Friday, this end, the right side of the 40 ohm resistor is closer to the positive terminal. So this is the high potential on that one. The right, left side of the 40 ohm resistor is closer to the negative end by this wire. So this is negative. So as I go across, I'm going from positive to negative. So I'm dropping a voltage. Same thing happens here. The left side of the current of the, the left side of the 30 ohm resistor is closer to the positive and the right side is closer to the negative. But since we went right, we're going the wrong direction. Since we're going the wrong direction, right? Since we're going the wrong direction, we're going to pick up our voltage. Did I do that right? Yes. Okay. All right, the outside loop. All right, pick a point to start. Let's pick a point here. Let's pick that point to start. I'm just going to follow it around the outside. So I'm going to gain 80 volts plus 80. We're going to drop 20 volts. So we're going in the same direction. We're good. We're going to drop, or not 20 volts, 20 I3 volts. Continuing around. Now we're going in the same direction. So we're going to drop. Go in the same direction. We're going to drop 30 I1 volts equals 0 because we're going to come back to that point. Good? So now we have 3 equations and 3 unknowns, and now we just have to do some algebra. Right? With 3 equations and 3 unknowns, it just becomes an algebra problem. In this case, it works out pretty nicely. If I look at these two, right? 45 minus 40 I2 plus 30 I1 and plus 80 minus 20 I3 plus, minus 30 I1. So right there, I can do by elimination, right? Here I can do this by elimination and get rid of the I1s. $125 minus 40 I2 minus 20 I3 equals 0. So I've eliminated one of our things.
Mr. Shuka would be negative 60 I2.
Negative 60, you're right. I can't add.
Oh, wait, no, my bad. No, because it's I2 and I3. My bad, never mind.
You're right.
So, separate terms. My bad.
I didn't write it out that clearly. We should be able to. Did I screw up my math somehow?
No, that's right. My bad.
No, I was looking at now using this equation and substituting in for I3, but then that just throws an I1 back into our equation. Where am I messing up my algebra?
Maybe we can try using the bottom loop, because I don't think
No.
we can solve the system of equations here.
Let's see where I would. No, we can, what we can do, if we substitute I3, if we substitute for I3, then we'll end up with a equation with an I2 and an I1, and an equation with an I2 and an I1. Right? If I make that substitution. So if I substitute in this spot, I got 80 minus 20 I1 minus 20 I2, right? Because I distributed the 20 across this, or the negative 20 across that, minus 30 I1 equals 0. And now I have two equations, this one and that one, that have an I1 and I2 in it. And now we're better. Now we're good. Two equations and two unknowns. All right? Simplifying that becomes 80 minus 20 I2 minus 50 I1 equals 0. All right. I'm going to play with colors because I can't. Bringing this equation to just so they're next to each other. 45 minus 40 I2 plus 30 I1 equals 0. We're at that point. Algebraically, good. I see an easy elimination if I double this equation, or I multiply everything by by negative 2. And then I'll get a positive 40 I2 and a negative 40 I2, and I can do elimination. Right? Does that make sense to everyone? So I take this equation and I multiply the whole equation by negative 2. I get negative 160 plus 40 I2 plus 100 I1 equals 0. Am I running out of space on the board? I can eliminate the 40 I2s. Right? I can eliminate the 40 I2s. They can go away, and I get negative 115 plus 130 I1 equals 0. Nice. Bring that over, divide 115 divided by 130 has got to be, I don't know what that's got to be, somewhere around 0.9. 115 divided by 130, 0.88. I'm going to round that up to 0.9. Good. So I1 is 0.9 amps. I can substitute back in somewhere, solve for I2. Now I have I1 and I2, and I can get I3. Right? Or substitute in, right? If I substitute in here, I got 45 minus 40 I2 plus 30 times 0.88 or 0.9 equals 0. That's 27. 27 plus 45 is 72. 72 divided by 40, I2 equals 1.8. If I did my math, if I'm doing my math in my head right. Right, 1.8 amps. And then, so if I1 is 0.9, I2 is 1.8, this has got to be 2.7 amps. Good? So, in terms of Kirkoff's law, right? We're writing, always write one of our formulas always has to be the current, and then pick two other loops. I don't care which two. And then do algebra to solve for our, right? Now you have three equations and three unknowns. Right? In theory, it could get crazy big. I'm never going to ask you, right? The three problems I'm going to ask you to do are never going to have more than three unknowns. In all of the, like I said, in the past 30 years, going back through FRQs, I only saw this twice on an FRQ on the actual test. And in both cases, it only had three unknowns also. All right, we're not going to get more complicated than that. All right, you think you guys can handle it? So you got about 20 minutes or so, give or take a little bit less than that, 18 minutes to start practicing and then continue. And then tomorrow we'll go over it. All right, there are three problems at the back of chapter 19. If I remember correctly, it's 27, 29, and 31 to work on. 27, 29, and 31. All right, I'm going to stop the recording.